Hi everyone, let us discuss this theorem. So in this theorem we have two functions f and g. Getting? So the given information is f and g, both of them are differentiable at point P. Additional information is g of p must be non-zero. Obviously it should be non-zero since it comes in denominator, so it should be non-zero. Then we have to prove that f upon g is also differentiable and its derivative will be this one. Okay. So it is same as the previous theorem which we have already seen in our previous video. We will start with the given information. Okay, so let me write it here. What we have f is differentiable at P. You are familiar with the definition of differentiability, right? So will you tell me what can we write here? So we can write by definition of differentiability, limit x tends to P, f of x minus f of P upon x minus P, its value is f dash of P. I will call it as equation number 1. Okay, so the second information is g is also differentiable. I can write the same thing for g. Also we have g is differentiable at point P. So therefore what can we write? Therefore limit x tends to P, g of x minus g of P upon x minus P is equal to g dash of P. Am I right? Yes. So this is equation number 2. Let me use the third information also. What we have? We have g dash, g of P not equal to 0 and g is continuous. G is continuous. Have they given this thing? G is continuous? No, they haven't given anywhere. Getting? But I have written here because the given information is g is differentiable. And we have seen one result, every differentiable function is continuous. So that's why I could write g is continuous. Understood? So this result we have already seen. If the function is continuous, it is non-zero at particular point, then in neighborhood of that point also function is non-zero. So therefore I can write implies g of x not equal to 0 in neighborhood of P. This is a very important thing. Since most of the times we take g of x and it will be in denominator, as you can see here, so it should be non-zero. That care we should take here. Okay, so that I have taken. Okay, so let us start the actual thing. The given part is over here. So our target is to prove that f upon g is differentiable. I will use the same definition to prove the function is differentiable. So for that we should consider a limit x tends to P, f by g of x minus f by g of P divided by x minus P. If this limit exists, we say the function is differentiable, that function f upon g is differentiable at P. Okay, so now our target is to prove that this limit exists, right? Let us operate function limit x tends to P, f of x upon g of x, here f of P upon g of P divided by x minus P. Will you guess the next step? I will cross multiply. Okay, so yes, I will cross multiply. What will you have? Limit x tends to P, f of x into g of P minus g of x into f of P divided by product of denominator g of x into g of P, as well as we have x minus P in denominator. Let me write it here. Okay, we have to apply the limit and we have to prove that that limit exists. But if you apply directly, we cannot solve the problem. Getting? And the very important thing, the given information. This information we should use somewhere. Getting? So for that we need to do adjustment, just like previous theorem. In previous video we already seen. Same type of adjustment I am going to do here. Okay. Small changes will be there. Limit x tends to P. What will I do? Let me think. F of x g of P minus f of P g of P plus f of P g of P, okay, minus g of x f of P. Have you understood what I have done? Simple thing I have done, that simply I have added and subtracted that f of P g of P, that's it, divided by, let me write a denominator, entire denominator, g of x g of P x minus P. Okay, So there is no more space to write. Make a screenshot of it first, then we will go further. So let us continue. Limit x tends to p. So simply tell me what can we take common from first two terms. We can take g of p common, right? So I will take g of p common. So f of x minus f of p, I am taking g of p common, g of p. And what can we take common from next two terms? I can take f of p common, okay, but as well as I will take minus sign also common. So minus f of p I am taking common. So in bracket we will have g of x minus g of p. Getting now? If you take minus sign common, that g of x has already minus sign, so it will be plus, and f of p has plus sign, so if you take minus sign common, it will be minus. Since if you solve the bracket, minus minus plus, you will have the previous step back. Divided by g of x, g of p, x minus p, okay. Now what shall we do? What will I do? I will divide separately by this bracket x minus p, okay. So see what will happen, limit, I am dividing separately. So if you divide separately, g of p is constant, we will keep as it is. I will take that denominator to this f of x minus f of p, x minus p, okay, and g of p as it is. Getting the point? I am dividing separately, as well as I will divide second term, f of p is constant, I will keep as it is, g of x minus g of p divided by x minus p, okay. So don't forget, there are two more terms in denominator, we haven't touched them. So those are g of x and g of p. I should write it here. That's it. Okay, that's it. It looks beautiful, and if you apply the limit, we can write their values. If you remember equation number 1, if you apply the limit, that is nothing but f dash of p. If you remember equation number 2, and if you apply the limit here, its value will be g dash of p. So we can directly put the values here, right? But see, there is no more space to write. Let me remove this part, and then we will finish this proof. Okay, so if you apply the limit, what will you have? Its value will be f dash of p, as I told you earlier, right? G of p is constant, will be as it is, minus f of p is constant, will be as it is. If you apply the limit to this bracket, its value will be g dash of p, divided by, if you apply the limit here, you will have g of p. The reason is same. G is differentiable. Every differentiable function is continuous. So that's why if you apply the limit to g of x, it will be g of p by definition of continuity. I am simply using the definitions everywhere, okay. And there is one more g of p is there. We apply the limit to this g of x, we got g of p, and this g of p is a constant. So I should write as it is. So let me mention the reason. The reason is from equation number 1 and 2. From 1 and 2. That's it. Okay, so it will be f dash of p, g of p minus f of p, g dash of p, g of p, g of p, g of p, its square will be square of g of p. I got this one. That's it. Yes, we want the same. We got it, right? So the most important thing is that limit exists. Limit exists, so that's why we say f upon g is differentiable at p. So let me write a conclusion. Therefore, f upon g is differentiable at p, and what will be its derivative? Derivative of f upon g at p is whatever the value we have got at the end, that will be its derivative. So f dash of p, g of p minus f of p, g dash of p, right, divided by g of p square. Yes, we got the same expression. So in this way we completed this proof. Make a screenshot of it, then we will stop. Thank you. Bye bye.